Section 2.3, Introduction to Limits, the tangent line problem. In this section, we will present the tangent line problem, and we will define the average versus instantaneous velocity. So what exactly is the tangent line problem? The problem of finding the slope of a line tangent to a curve at a point was one of the two motivating problems in the development of calculus. We will use the problem below to explain and introduce the concept of a limit. So the question here is, suppose we want to know the slope of the line tangent to the function f of x, which is equal to x squared at x equal to 1. This is a parabola. We want to know the slope of the tangent line. So let's get a picture going so we can really understand what's going on here. So first of all, drawing the parabola, we can see that it passes through some points on the xy plane, in particular the point 0, 0 at the origin. It passes through the point 1, comma 1. When x is 1, the y is going to be 1. And so on and so forth. For example, 2, 4 over here. So the question is, we want to know the slope of the tangent line at 1, so we want to know the slope of the line that touches the curve basically exactly once, and that's when x is equal to 1. So the line would pretty much look something like this right here. We want to know the slope of that line that touches the curve at x equal to 1. So when x is equal to 1, what's the slope of the line that touches the function f of x, which is equal to x squared? So that is what we call the tangent line, and in order to find the tangent line, we will be using limits and derivatives later on. But for now, we don't have those tools, so how can we go about finding the slope of this blue line? Well, the process is going to be to find the slopes of secant lines and get better and better approximations. So what do I mean by that? Here's what I mean by that. We will draw multiple lines passing through the point 1 and another point on the graph. So do that multiple times and repeat the process over and over again until we have enough lines. And as we do this process over and over, eventually we will get closer and closer to the blue line. Once the points are close to one another, the line that we draw and the blue line will sort of overlap. So the closer we are, the better the estimate is. So first we'll start with the line far, far away, and that will be obviously a different slope than the blue slope. Then we will pick another point on the graph and connect it with the point at x equal to 1, find the slope of that line. Then we get the point closer again, and we will keep the process over and over until we have the line in blue, and that will give us the actual slope. So in this case, the process is going to be like a table. And what we're going to do is basically determine the slope of the secant line between the points that have these x coordinates. For example, the first time we do this, we're going to pick the point that has x coordinate at 1, so this first point, and the second point is going to be that one right there. We're going to find the slope of the line that passes through those 2 points, and obviously it's not exactly the slope of the blue line, which is what we're looking for. But that's why we're going to do this process again and again and again and again until we are super, super close and we finally can make a conjecture or like an estimate, an educated estimate on what the slope of the blue line could possibly be. So how do you find the slope of a line? So remember, the slope of the line is given by y2 minus y1 over x2 minus x1. Keep in mind that y2 and y1, sometimes in calculus, we don't write those letters. Sometimes we write f of x2, for example, and instead of y1, we would write something like f of x1. So in other terms, plug the x that you're given into the function and get the value of y. And the x2 and the x1 are going to be these numbers over here. So x1 in this case is going to be 1, and x2 in this problem is going to be 2. Then we'll do this again with x1 being 1 and x2 being 1.5. And then again with x1 being 1 and x2 being 1.2, and so on and so forth. So notice how we're always keeping the same x1 for every estimate. And we're going to do this 5 times, and we're keeping the same x1. So the formula, the fraction that we're going to have, will have the same number on the denominator x1. And the y1 will always be the same because that's just plugging in x1 into the function f of x. Speaking of which, remember the function f of x is equal to x squared. So what happens when I plug in this x1, which is the value 1? So, well, I get 1 squared, and that's exactly equal to 1. So this number here is going to be 1 for x1, and the number y1 is also going to be 1 when we do this estimate. The other two numbers will change depending on the numbers we have in the particular column. So for example, in the first column, x2 is supposed to be 2. So this number here will be 2. And the y2, how do we get it? We plug 2 into the function. So if I plug 2 into the function, I'm going to end up with 2 squared, which is going to be 4. So for my first estimate, the slope of the secant line that passes through the points where x is equal to 1 and y is equal to, x equal 1 and x equal to 2 is going to be like this. So first put the y2, then the y1, divide them by the x2, which is 2 in this case, and finally the x1. So keep in mind that this number on the denominator, the 1, represents the x1. This number on the numerator represents the y1, and the x2 is going to be 2, and that's the number on the denominator. And finally, the y2 is going to be this value right here. So the y2 and the x2 will change every time we do this process. So in this case, m will be 4 minus 1, which is 3, divided by 2 minus 1, which is 1. So in other terms, m is equal to 3. So far, what we're saying is if we pick the first number to be x1 at 1 and x2 at 2, the slope of the line connecting those two dots, that line, the slope of it is basically 3. And that's not a great estimate because the points that we chose are really far from each other. They don't represent the slope of the secant. They don't represent the slope of the tangent line, which is what we're looking for. So this is why we're going to do this process again and again, multiple times. So moving back to the bottom, we have another estimate that we have to evaluate. So remember, it's y2 minus y1 over x2 minus x1. So I'm going to put the minuses. x1 I already know is 1. y1 I already know it's also 1. So y1 is the number there. That's always fixed. And x1 is always the same value, which is 1. So now what do I need to do? I need to figure out what the x2 is. And in this case, x2 is going to be 1.5 because that's the estimate we're choosing. And finally, I need to know the y2. So what would happen if I plugged in 1.5 into the function? So 1.5 squared, and we can use a calculator to evaluate that. So using my calculator, I will type in 1.5 and then all squared, and the answer is going to be 2.25. So that goes on the numerator, 2.25. And all I have to do now is just subtract all these numbers and divide them out and get the estimate for m. So since I have my calculator turned on, let's go ahead and use the calculator to estimate. And as we can see, the estimate will be 2.5. So 2.5 is the slope of the line that connects 1 and 1.5 with each other. So 1.5 is somewhere roughly here on the x-axis, and if I trace it to the curve, that will be that point right there. So if I connect these 2 points with one another, I'm going to get some kind of a line. We know it's slightly different than the blue line, and its slope is the one we just determined. So obviously, it's not close enough, so we're going to get closer even further. So the next estimate, we'll be using 1 and 1.2. So 1.2 is going to be here, which puts me really close on the curve to the original point, and so let's see what happens. So the process is the same, so let's go ahead and calculate some things. So x2, x1, y2, y1. So let's start with the minuses, 1 and 1. Those are the original values for x1 and y1. And in this case, what I'm doing is I'm choosing 1.2 for my x2 value. So let's put that in the denominator, and we need the numerator. It's 1.2 squared. So what is 1.2 squared? So it's 1.44. Great. So we put that in the numerator. And now we are ready to basically estimate the value of the slope of the secant line. So this is not exactly the tangent line. It's the secant line. So let's see. Calculator time again. And according to my calculator, the number should be 2.2. So great. Let's put that on our notes. So 2.2 is the next slope. So as we can see, the value went from 3 to 2.5 to 2.2. So if you want, can you make a prediction about what it's going to be over here at the end without doing the math? See if you can guess what the number here should be. So there should be a pattern. You should be able to kind of guesstimate or estimate what it's going to be. But for now, while you do that, let's calculate the other two values. So I'm just going to do it all together without doing too much coloring here. So 1, 1, these are always x1 and y1. And for this particular fourth column, I'm going to be using 1.1 as my second point, and I need the square of 1.1, and the square of 1.1 is 1.21. So there's the numerator, 1.21, and now we can just use our calculator to estimate the value of this whole fraction. According to my calculator, the value should be approximately 2.1. Okay, great. So let's transfer that to here. So 2.1, and like I said earlier, there was some kind of a pattern. So were you able to guess what the next one is? If not, let's see. So it's 1.05, that's my x2, and I need to square the 1.05. So let's do that on the calculator. And I'm getting 1.1025. So let's plug all the whole fraction in right now. So let's subtract 1 divided by 1.05 minus 1, since we have to do that anyway. And my estimate is 2.05. Okay, so the m that we're looking for is 2.05. And let me just record what the numerator was when we found it. So as you can see, our estimates went from 3 to 2.5 to 2.2 to 2.1, and then finally 2.05. We only did this 5 times, but you can do it as many times as you need. And it seems like if the first point is 1 and the second point is 1.05, then the points are going to be super, super close to one another, and the line that we get is virtually the same as the blue line. And it seems like its slope is, we're finding out that the slope is really 2.05. So now the question is, if you were to guess at this moment in time, we don't have any tools yet today, except for this one that we're doing, just estimating and guessing. But if you were to guess the slope of this blue line, what number would you assign to the slope? And so logically speaking, since I'm noticing that the value is 3, then 2.5, then 2.2, then 2.1, then 2.05, it seems to me like a good idea would be to estimate that the slope of the blue line is probably, I don't know, maybe 2. And that's what we call for now the conjecture. So conjecture in math just means that it's a hypothesis that you haven't tested yet and you haven't confirmed. But all the signs, like these last 3, 4 numbers, are all roughly 2. I mean, this one maybe you can argue that it's too far from 2, but the other 3, the closer I am to 1, the closer the number is to 2. So you can repeat this problem multiple times, and you'll see that the number eventually becomes 2 if you do it infinitely many times, but obviously we don't have that kind of time. But for now, the guess is that the slope of the tangent line should be maybe equal to 2. So the process of moving the x value closer and closer to a point without actually reaching the point, so obviously I cannot put 1 and 1 on the denominator of this fraction or that fraction or anything, so I always have to choose a different value on the second coordinate. I can't pick 1 and 1 because my denominator would become 1 minus 1, which is 0, and you can't divide by 0. But the process of doing this over and over again is basically what we call in math the limit. And this is going to be one of the foundational concepts in our study of calculus. Okay, so now let's talk about an application of this limiting process, and this application involves the average versus the instantaneous velocity. So you may have heard in a previous course in an algebra class that the distance is equal to the rate times the time, or that the distance is equal to the velocity times the time. Either one is acceptable. This one is the more common one. Distance is equal to rate times time. Rate in this particular instance just means the speed, or the velocity, I should say. And so if I solve for the r or the v in these equations, so like for example, if I take this equation, it says d equals to v times t. If I want to solve for v, if I want to isolate the v itself, I would have to divide both sides by t, and dividing both sides by t cancels out the t's from here and leaves me with the velocity equal to the distance divided by the time. That's what we're basically writing on the second line of this problem. Why is that useful? You'll see in a moment that we're going to be given a function that represents the distance traveled, and we're going to want to know the speed or the velocity at a specific instant. And so this is why I'm bringing this up right now. Now, how do you calculate the average velocity? Basically, the same way we calculated the slopes of the secant lines on the previous page, right? We're just going to take two numbers, put them on the numerator, take two numbers, put them on the denominator, and just divide out the results. So let's give that a shot. Let's see what's happening in example number 1. So it says, suppose a rocket is launched vertically upward from the ground with a speed of 120 feet per second. The height of the rocket above the ground, meaning its position, and they're calling position in this problem S of t. So the position S of t is given by the function, which is S of t equal to negative 16t squared plus 120t. And I'm being told that S has the unit in feet, and that represents the number of feet above the ground, and t is measured in seconds in this problem. Okay, so the S is measured in feet, so the units we're going to be using are feet and second. So the first thing I want to do is draw the graph of this function in an appropriate window. So let's do that using our calculator. So what we're going to do is take this function and put it in our calculator. Obviously, our calculator doesn't have the letters s and t. So what we're going to do is put it into y1, like negative 16x squared plus 120x. So that's what we're going to type into the calculator. And then let's see what happens and how we can reach an acceptable window. In this particular case, I'm kind of giving you the dimensions, but if you didn't have the dimensions in front of you, how can you go about it? Let's go to the calculator now. So from the main screen of your calculator, you're going to click on the top left corner, the Y, and this is where we go to always graph anything. So we're going to type in negative 16, and then we're going to hit the same key that we always do for the variable, and I want that to be squared plus 120x. So for now, let's click on zoom number 6, and when we do that, we see like almost two vertical lines. But this is not an appropriate window, that's why we're seeing this. So what we want to do is modify the window so we can see the full graph. We don't want to think that this is two parallel lines or two lines, when in reality it should be actually a parabola. So one thing we could do is go to zoom, and one of these is a special kind of window, the one called zoom fit. It's for me option 0. The zoom fit on your calculator will basically tell the calculator, hey, you do your best to find the best window for me that fits the whole graph as good as possible. So it's different than the standard zoom that we usually use, which is option number 6. That one will always put the window from negative 10 to positive 10 on both the x and y coordinates. The zoom fit will tell the calculator to decide itself what the best option is. So let's see what the calculator comes up with when we click on zoom fit. So you can either click 0 on your keyboard or just go up and down until you find it, then click enter once you have selected it. And as we can see, now it's starting to look more like a parabola. Now obviously the rocket is going up in the air, so it's not going to have negative distance. So all of the negative y coordinates basically are useless to me. So I'm going to go to my window and I'm going to remove the negative 2,800 that I see next to the y minimum. I know that the distance traveled cannot be negative, so why do I want to see all those negative values? I'm just going to put 0 there, and let's take a look at what the graph looks like now. So an even better looking parabola, so that's awesome. And again, the first half of the screen where all the x's are negative, it doesn't look like we have a graph, and those represent the time being negative, and time can't be negative. So again, let's make some adjustments. Go to window, and let's make the x minimum 0. Right? Remember, x is t for us, and t is time. Time can't be negative. So that's why I'm putting 0 there and 10 next to the x maximum. That was already decided. So that's great. And let's click on graph. So there we go. We have a better looking picture. And if we want, we can make some more adjustments so we can see the top of the parabola a little bit better. And maybe we want to remove some of the extra empty space on the right side of the graph. We can do all that with the window settings. So I don't need to necessarily go all the way up to 10. It seems like 9 or even possibly 8 would be a good place to stop. Maybe I want to see the top of the parabola, so instead of 224, let's make it, I don't know, maybe 250. And again, click graph, and now our parabola looks really, really nice. Okay, so one thing we could do here is click on trace, and that puts us on the actual parabola, and we can kind of walk around and see how high and how low the points are. So right in the middle, there's a high point right there. It looks like the point is going to be at x equal to 3.75, y equal to 225. So we can take advantage of that when we're plotting this or when we're transferring this from the calculator to our page, basically. Another thing that might be interesting is to find where it touches the x-axis. So if you continue walking all the way to the right, you might be eventually able to reach that point. It might take you a little while, but let's see. It should be somewhere around maybe 7.5 or something like that. But let's see. Yeah, exactly. 7.5 on the x coordinate gives me the y coordinate equal to 0. I can see that on the bottom of my screen. Okay, so with all that information in mind, let's transfer this graph to our page. Okay, so when you do this, it doesn't have to be perfect. I mean, if we wanted a perfect graph, we would just stick with the calculator screen and just look at the calculator screen. We just want to approximate what the graph looks like here, and I labeled a few interesting points. For example, when time is 0, our position is also 0. When the time is 7.5, we are also sitting on the horizontal axis. We're crossing the horizontal axis, the time basically. So the whole flight pretty much started at 0 seconds and ended after 7.5 seconds. We went up, then we went back down, right? So we went up to the height of 225 feet. That's what we're being told over here with this parabola reaching that height. That's the vertex, by the way, the highest point on the parabola. So our rocket was on the ground, it went up, and then it went back down, and it went up basically 225 feet before it hit the ground again. So now that we understand what's going on, they want us to look at example or the part 2 of this problem, and they want us to find the average velocity of the rocket between time 1 and time 3, then time 1 and time 2. So at time 1, we're somewhere over here, and time 3, we're somewhere over here. They want to know the average velocity. So how fast were we going between these 2 points? Well, that's exactly what we discussed above in the previous paragraph. In other terms, what they want me to do is just find the slope of the line that connects the points where t is 1 and t is 3. So let's go ahead and do that. So how do I find the average velocity? So I'm going to write average velocity, average velocity, and I'm going to determine it by doing the following. I'm going to find s of 3 minus s of 1 divided by 3 minus 1. Remember, basically, it's y2 minus y1, except I can't use the letter y in this problem because they're writing s for me instead of y. And these guys right here are x2 and x1, but again, I can't use the letter x because they're writing t's for me. So this is t2 and that's t1. So that's all we're doing here. It's basically the same thing that we did on the previous page, except the function is a little bit more complicated. It's not just a nice x squared parabola. So to find S3, I'm going to take my function S and I'll plug in 3 into all the places where I see the 3. The t. And we can use our calculator to eventually find what this value is. For S1, it's basically the same idea. I'm going to take my calculator and plug all these numbers in and see what I get for the solution. Later on, I have to do the same thing with t equal to 1 and t equal to 2. So you know what? Let's do SF2 right now. It's going to be negative 16 and then 2 squared plus 120 times 2. So why am I putting all these numbers in? So remember, the first value is the same. That's why we're putting 1 there, and that's why we're putting 1 on the denominator. And when we evaluate it, there's going to be some number that appears, and that's going to be like basically the y coordinate. That's what we place on the numerator. And we're going to do this twice, basically. And the other number we're plugging in is 3 for the first time. And when we plug it in, there's going to be some value that comes out. We're going to be calling that S of t, or SF3 in this case, and that will be placed on the numerator over here. Okay, so let me show you how you can find these numbers very quickly without having to type everything into the calculator. So you should already have the parabola graphed on your calculator, right? It should be already there. What we could do is take advantage of the trace command and just plug in, for example, 1. So click trace on your calculator first, and then just click 1 on your keyboard, then hit enter. And it will tell you that when x is 1, the y is 104. So basically what the calculator is doing is it's putting 1 into the whole equation, and it's telling you the output. The output is 104. And so when I do 3, it will give me 216. So again, the way it works is you plug in the parabola, you graph it, you figure out the dimensions of the window that you care for, and then finally you click trace, then you click 1 on your keyboard, and that tells you here's the place where x is equal to 1 and the y is 104. So let me write that down. When x is equal to 1 or when t is 1, I get 104 as the output. So that's great. And so we can use that here in this fraction. And when the time is 3, what do I get from that? When I put 3 into my calculator, I get 216. So great, so the number here is going to be 216, and so that number is going to go on the numerator of the fraction. So with the whole thing done, let's see, I'm going to have 216 minus 104 divided by 3 minus 1, that's going to be 2. It's just simply 2. And now we can estimate what the value is, again, using the calculator. And I'm getting 56. So 56 is my first solution for the first problem. And what's the unit? Remember, these guys on the numerator represent the y, or the height, or the distance traveled, so that's going to be feet. And they're being divided by things, numbers that represent time. So this is going to be feet per seconds. So the average speed between 1 and 3 seconds for my rocket was 56 feet per second. And let's just put a box around all this. Okay, so what I'm going to do next is basically repeat the same process again, but with the other T1 and T2. So let me shrink this down a little bit so we can fit everything else. I'll move it here for now. And let's do it again. So if I want to know the average velocity between this time, we want to go between 1 and 2. So we're going to get the numbers closer to one another. So there's a new line that will happen when you connect those points. We want to know the slope of that line. So again, it's going to be a fraction. The slope tells me to put y2 minus y1, but remember, we're not using those letters. We're using s because that represents the y coordinate. S2 minus S1, those numbers are from here. And then again, I divide by the same numbers again into the denominator. So this is just the rise over the run. And so I need to know what S2 is and what S1 is. And I already know the denominator is going to be 1 because 2 minus 1 is 1. When I plugged in 1 into the S earlier, we got 104 for the value. So that's, we know it's going to be 104. All we're missing is S2. So you can calculate it by hand, or you can use your calculator again to estimate the value. So let's use our calculator. I'm going to go to my graph. My parabola is still there. I'm going to click trace, then I'm going to click 2 on my keyboard, then hit enter. So that puts me at the place where the time will be 2 and the output is 176. So my rocket is 176 feet high. So I'll just put that into this entry over here, and then 176 there. And now all you have to do is just subtract 176 minus 104 and divide it all by 1. And so 72 feet per second is the final answer there. Okay, so that is the solution. I'm going to, again, move things around so that we can see both solutions for this problem together. These are supposed to be the same problem. Okay, so that's it for part 2. We're basically finished. So the average velocity between time 1 and time 3 was 56. The average velocity between time 1 and time 2 was 72 feet per second. So we were going faster at the start of the launch than we were when we waited a lot longer. All right, it kind of makes sense. So remember, these lines were not the tangent lines because, first of all, we connected these 2 points, then we connected these 2 points. So these are not tangent lines because the line that we're choosing crosses the curve in 2 different locations. So what if I wanted to know the slope at 1? So what if I want to know the instant speed when the time is equal to 1? So exactly at 1, how fast my rocket was going. So if you were sitting inside of it and you had a speedometer, you would just look in front of you and it would tell you your actual speed, but we don't have that here. We're not sitting in the rocket, so how can we go about it? Well, we will do exactly what we did on the previous page, and we will do exactly what we did over here a couple of times. We're going to repeat it many, many times, except every time we repeat it, we're going to keep the time 1 placed constant, and we're just going to take our second point and get it closer and closer and closer to the other point. So we're going to choose different times, and we're going to need to get them as close as possible to 1 without actually touching the time 1 itself. And that's what this table here is supposed to do for us. So I'll just do the first couple so you can see what we're going to be doing. So I'm going to be looking for the average speed or average velocity. This time I'm just going to call it m just because I can't fit all the words and all the numbers and everything in here. So for the first one, I'm choosing time 2 minus time 1. So I need s of 2 minus s of 1 in the numerator. And as you can see, that's the one we just did. So instead of doing this, I'm just going to write the numbers, 176 minus 104 divided by 2 minus 1, and we determined earlier that the speed there was 72 feet per second. So next I'm going to do again the same thing for 1.5 and 1. So I'm going to do 1.5 minus 1 on the denominator. I know that 1 time is 1, and I plug it into the function. The answer is going to be 104. We traced it earlier, and we figured that out. So now what about this value? What would happen if I trace 1.5? Okay, so back to my calculator, I'm going to click trace, then I'm going to click 1.5, and it's given me 144 as the output. So that's what's going to go on the numerator there. So 144 minus 104 divided by 1.5 minus 1. The answer will be 80. So be careful when you're putting things in. You need to use parentheses because we have multiple numbers in the numerator and denominator. But in this problem, I'm getting m, the slope or the average speed between 1 and 1.5 seconds. The average speed there was 80 feet per second. So again, repeating everything one more time. So 1.1 minus 1, these are the x2 and the x1, or the time 2 minus time 1. I know that when x is equal to 1 or when time is equal to 1, the output is 104. But what about the value that corresponds to the output of 1.1? So I need the calculator. So graph and then trace 1.1, and I'm going to end up with 112.64. Okay, you know what? I'm just going to round it to 112 roughly. So I'm going to put approximately equal to, and I'll put 112 right here. So now I need to do 112 minus 104 divided by 1.1 minus 1. As you can see again, the number is 80 one more time. And all right, so let's write m is approximately 80 feet per second. So remember I rounded earlier, it wasn't supposed to be 112 exactly, so I'm just going to put the not the straight equal sign, but the squiggly equal, because that's an approximation. Okay, one final time, and then we can make a conjecture about the actual speed at the time when t is equal to 1, so at 1 second. So again, the y2 and the x2 and the x1 and so on and so forth. So what do we do here? We have 104 already on the numerator. We need to know what the value for the y-coordinate is going to be when the time is equal to 1.01. So let's go back to our calculator. Click trace 1.01, and it's given me 104.8784. I'm just going to say 105, just rounding it off. So I'm going to use the approximation and put 105 there. So 105 minus 104 divided by 1.01 minus 1. So what do we get on our calculator? Okay, so this time I got 100. So 105 minus 104 divided by 1.01 minus 1 is 100. And this is because I rounded. If I was a little bit more careful, the numbers would show a better pattern, but we did not do that. So we're going to say 100 feet per second. And you know what? Let's just, if we can, try to guess what the slope at the tangent line is, right? So at the time when t is equal to 1, what do you think the slope should be? So if you, after doing all this work, what is your conjecture? What is your hypothesis? So if I were a betting man, which I'm not, I would probably say that I think the slope should be 100 at the time when t is equal to 1. And that's because I picked these two numbers really, really close to each other, and the result was 100. And it kind of went from 72 to 80 to maybe like 85 for the middle one. We rounded off a little bit, and then it became 100. So it seems like it's the numbers are approaching 100 as I do this process over and over. Now, if I wanted to be super exact, instead of picking 1.01, I would pick 1.001, for example. Or if I wanted to be even more exact, instead of that number, I would pick 1.000001, for instance. And I would just repeat this process as many times as I need until I've confirmed that my slope is possibly 100 feet per second. So we think the instantaneous velocity is 100 feet per second, and in the future we will decide if this number is actually correct or not. Okay, by the way, in reality, this is an estimate, but it's going to be actually off from the real thing. I know a little bit more calculus than you do at this point, and I know that the real answer is supposed to be 88 feet per second. And why are we off so much? Again, that's because we rounded here. Remember, this 112 wasn't supposed to be 112. It was supposed to be some kind of decimal. Same thing again with the 104, and that results in our answers being a little bit messed up. So the real number that we're going to basically eventually find is going to be 88 feet per second. And that's going to represent the actual speed when time is equal to 1. So it's not the slope of the secant lines, it's actually the slope of the tangent line.